Hi, hello dear students. Welcome to physics class of PO2. We have been discussing about the chapter nuclei. In the previous class regarding the chapter nuclei, I have given about the introduction part. We have discussed about the introduction part, that is about what is an atomic number, what is an atomic mass number, and also the properties of the nucleus such as nuclear size, nuclear mass, nuclear charge, nuclear density. And also we have defined about what are isotopes, isobars and isotones, right? With all these introduction parts, we are going to discuss here the next point of the syllabus, that is Einstein's mass energy relation. We are going to discuss here, that is E is equal to mc square, and also we are going to discuss about the nuclear binding energy. What is the binding energy of the nucleus, and what is mass defect, and also about the specific binding energy. So here first point, what is Einstein mass energy relation? E is equal to mc square. So we have the law of conservation of mass and law of conservation of energy, right? We have the separately two conservation laws here related to mass and energy, law of conservation of mass and law of conservation of energy. So according to law of conservation of energy, so energy can neither be created nor be destroyed, but it can be converted from one form to another. Again, from this equation, Einstein's mass energy relation is equal to mc square. This Einstein mass energy relation, from this the mass and energy are interconvertible. That means what? The energy can be converted into mass and mass can be converted into energy. That is what the Einstein mass energy relation. So according to Einstein, the energy equivalent E of mass m is given by, suppose a body of mass m, right? Its energy is given by what? E is equal to mc square. So how we are going to calculate the energy of the mass m? E is equal to mc square. What is C here? C is the velocity of light. C is velocity of light in air or vacuum. Its value, you know, it is 3 into 10 to the power 8 meter per second. Right? So, according to Einstein's theory of relativity, any body is a source of any body of mass m is a source of energy, even if it has no kinetic energy or potential energy. Due to its mass alone, it is a form of energy according to Einstein's theory of relativity. He explained and he given the relation that E is equal to mc square, right? So the energy present in a body of mass m is given by E is equal to mc square, where C is the velocity of light. So the energy is released when some amount of mass is lost. Suppose a body of mass, even if a small mass is lost, that is converted into energy. That means what? The energy and mass are interconvertible. So we have the separate law of conservation of mass and the conservation of energy that can be combined into a single principle, that is what? The law of mass energy. The equivalent of mass and energy given by the relation E is equal to mc square. So separate laws are combined into a single law, that is what? Law of equivalence of mass and energy. Law of conservation of equivalence of mass and energy. E is equal to mc square. Right? Now let us see some examples for conversion of energy into mass and mass into energy. For example, every particle has its antiparticle. For example, we have the electron, right? It is having a certain mass m. Mass of the electron is m. So we have the another particle of this electron. Antiparticle of this electron is positron. That is called as what? E plus. So E minus is electron and E plus is called as what? Positron. E plus is called as what? Positron, and E minus is called as what? The electron. And here the mass of the electron and the mass of the positron is same, but only the charge of the electron is minus and the charge of the positron is plus. But their masses are equal. That is electron E minus, this positron E plus. Charge is positive for positron, charge is negative for electron. Now here we can explain the law of conservation of mass energy example by taking this electron and positron. That is called as annihilation of matter. The example is now here we can call it as what? The annihilation of matter. You all know that what is a matter. Anything which occupies a space and has a mass, that is called as what? Matter. So E minus and E plus is also matter here, is having the mass M E. Masses are equal. Now when this E minus, that is the electron, and positron E plus, when these two come close to each other, the electron and positron come close to each other or collide each other, these two destroy. That means what? They destroy and form the what? The gamma rays. So gamma rays means what? It is having the energy. Gamma rays having the energy. So here the mass, 2 times of the mass of the electron is converted into what? The energy. That is the gamma ray. Right? When this electron and positron come close to each other, they annihilate. Annihilate means what here? Destroy it. Annihilate means what? The destroy. When this electron and positron come very close to each other or collide each other, they destroy and forming the what? The gamma rays. So here the 2 times of mass of electron is converted into energy according to this relation E is equal to mc square. Here you can write the energy released during the process of annihilation of matter is given by E is equal to 2 times of mass of the electron into c square. So when we have lost the electron and positron, that is converted into energy equivalent is equal to 2 times of mass of the electron into c square, and it is that energy comes in the form of gamma rays. Right? This is an example what we can give for the conversion of energy, conversion of mass into energy. Right? Conversion of what? The mass into energy. Again here we can give the examples for the conversion of the mass and energy into mass. That is, we are going to explain here about the nuclear fusion and the nuclear fission. So nuclear fission, nuclear fusion, so binding energy. So all these are the examples for what? The conversion of the mass into energy. So here during the formation of nucleus from its nucleon, some mass is lost. That we are going to explain here about what? The mass defect. So we have to discuss here what is the mass defect, right? What is mass defect? We are going to define it. Then we are going to discuss about what is binding energy, nuclear binding energy, and then we are going to explain here is about the nuclear specific binding energy. And you know that during the process of nuclear fission, right, the heavy nucleus splits into lighter nuclei during the process of nuclear fission, right, and which releases the energy of the order of 200 mega electron volt during the process of nuclear fission. Right, that energy can be used for the destructive purpose, for the constructive purpose also. Destructive purpose means what? For atom bomb. Atom bomb is an example that here you can use, that is used for what? The destructive purposes. Constructive purpose, what we can use, the energy released is what? The nuclear reactors. The energy released during the process of nuclear fission, that is used for the destructive purpose as well as for the constructive purpose. So example for the destructively, as in an atom bomb. Atom bomb is an example that is used for the destructive purpose, that is energy released during the process of nuclear fission. Constructive purpose means it is used for in the case of nuclear reactor, right? So in the next classes we are going to explain in detail about the nuclear fission with examples, nuclear fusion in detail with the examples we are going to explain here. Now I am going to explain here about what is mass defect and what is binding energy, nuclear binding energy and nuclear specific binding energy. I am going to explain here mass defect, binding energy and specific binding energy. I think all of you have followed this. What is Einstein mass energy relation? That is E is equal to mc square. That means what? The mass can be converted into energy. Energy can be converted into mass according to this relation. Some amount of mass is lost means that is converted into energy according to this relation. E is equal to mc square. Right? The examples for Einstein mass energy relation or Einstein mass energy conversion examples are what? The annihilation of matter. During the process, the electron and positron come close to each other. They destroy and they are converted into what? The energy as a gamma rays. Right? Nuclear fission is also an example of E is equal to mc square, the Einstein mass energy relation. Here the mass is converted, in case of nuclear fission also, mass is converted into energy, nuclear fusion also, and again in case of binding energy. Now I am going to explain here is about the binding energy and mass defect. So now let us see here what is mass defect and binding energy. So what is mass defect? That we are going to define here. The difference between the sum of masses of the nucleons forming the nucleus and the rest mass of the nucleus, stable nucleus, right? So as you all know that, let us take an example here. XZA, the symbolic representation of the any nucleus of an element. Let us take an example of nitrogen here. Its atomic number is 7 and mass number is 4. That means what? This nitrogen nucleus is formed by the nucleons, that is equal to what? 7 neutrons and 7 protons. Nitrogen nucleus is formed due to these nucleons, that is 7 protons and 7 neutrons. So what we are going to say in case of mass defect here, the difference between the sum of masses of the nucleons forming the nucleus and the rest mass of the nucleus. Right. So that what we are going to define here. M into, that is the mass of the proton is mp, with 7 protons are used during the formation of the nitrogen nucleus. Again 7 m. Right. In general form, what we have written here, that is equal to what? ZMP plus A minus ZMN. Right? This is what the sum of masses of the nucleons. Right? The sum of masses of the nucleons. And if you have taken from these nucleons, this stable nucleus, stable nitrogen nucleus is formed. We have taken the example. Its mass is equal to M. Right? That is the rest mass of the nucleus. Now what is mass defect? We are going to define here. Delta M is equal to ZMP plus A minus ZMN minus M. That means what here? The sum of the mass of what? The mass of sum of the nucleons we have taken, then the rest mass of the nucleus. That is, this is what this capital letter M is what? The mass of the nucleus after forming the stable nucleus. This is what? The mass of the nucleons in the free state before forming the nucleus. Right? So some amount of mass is lost during the formation of the nucleus from its nucleons, its constituent nucleons. In nucleons in the stable nucleus form ಆಗಬೇಕಾಯ್ತಂದ್ರೆ some amount of mass loss occurs. That loss in mass or missing of mass, miss in mass, that is called as what? what? The mass defect. That is converted into energy. That is called as what? The binding energy we are going to define. So as we have discussed in Einstein mass energy relation, if some amount of mass is lost, that is used as what? The energy, that is converted into energy. So then what is binding energy? We are going to define. So according to Einstein mass energy relation, this loss in mass or missing mass, that is converted into energy, that is called as what? The binding energy. That binding energy EB or EB is defined as what? Delta M into C square. I think the first point is clear. What is mass defect? The difference between the sum of masses of the nucleons forming the nucleus. So this is what the sum of masses of the nucleons, they are going to form what? The stable nucleus. And then you by using these nucleons, the stable nucleus is formed here. But if we measure the mass of this rest mass of the nucleus, which that mass is always less than the sum of masses of the nucleons in the free state. ಇವೆರಡೂ ಡಿಫರೆನ್ಸ್ ತಗೊಂಡಾಗ್ರಿ ಏನಾಗ್ತದೆ ಅಲ್ಲೇನೋ ಮಾಸ್ ಲಾಸ್ ಆಗಿರಲಿಲ್ಲ ಅಂತಂದ್ರೆ there is no loss of mass, then the sum of the masses of the nucleons must be equal to the mass of the stable nucleus. Equal ಆಗಿರಬೇಕಾಗಿತ್ತು, but that is not equal, right? Some amount of mass is lost. ಇವೆರಡೂ equal ಆಗಿದ್ದಾಗ delta m is equal to 0 ಬರಬೇಕಾಗಿತ್ತು, but here we are getting positive. But we are getting positive here. That means what? Some amount of mass is lost during the formation of stable nucleus from its nucleons, constituent nucleons. Now that mass is called as what? The mass defect, that delta m. Then that should be converted into energy according to Einstein mass energy relation. That is called as what? The binding energy. Binding energy is equal to what? Delta m into c square. Right? Delta m into c square. Now what is binding energy then? What is binding energy, or it is also called as what? The nuclear binding energy. What is the nuclear binding? That means this energy required for what then? This energy is required for what? To bind the nucleons, right? Inside the nucleus. The amount of energy required to bind the nucleons and to form the stable nucleus. That is called as what? The binding energy. Nuclear binding energy is what? The energy required to bind the nucleons to form the stable nucleus. ಇಲ್ಲಿ ನಾವು nucleons ಇಂದ nucleus form ಆಗ್ತದೆ, right? ಈ nucleons form ಆಗಿ, right, bind ಆಗಿ nucleus ಆಗಿ form ಆಗಬೇಕಾಯ್ತಂದ್ರೆ some amount of energy ಬೇಕಾಗ್ತೈತ್ರಿ. ಅದರ ಸಲುವಾಗಿ ಏನಾಗ್ತದೆ ಇಲ್ಲಿ some amount of mass loss ಆಗಿ ಅದು energy ಆಗಿ convert ಆಗುತ್ತೆ. That energy is used, that converted, this mass is lost, that mass is used for what? To form the nucleus from its nucleons. Right? Binding energy means it is the amount of energy required to bind the nucleons to form the stable nucleus. Or it is also called as the amount of energy required to break the nucleus and to form its constituent nucleons. ಇಲ್ಲಿ nucleus ಅನ್ನು break ಮಾಡಿ nucleons ಅನ್ನು separate ಮಾಡಬೇಕಾದರೂ ಕೂಡ ಏನಾಗ್ತದೆ? This amount of binding energy is required. During that time, that energy is converted into mass. And here the mass is converted into energy. So that is an example here, right? Binding energy means the amount of energy required to bind the nucleons to form the stable nucleus, or it is the amount of energy required to break the nucleus and to form its constituent nucleons, right? So these are the two important points here. What is mass defect and what is nuclear binding energy? How we are going to calculate the nuclear binding energy? From this equation, EB is equal to what? Delta m c square. Right? Now let us take one example here to calculate the mass defect and to calculate the nuclear binding energy by taking an example. So now let us calculate here the mass defect in case of the helium nucleus, and also then we will calculate the binding energy of the helium nucleus also. So here helium nucleus, if I take an example, Here it consists of what? The 2 protons and 2 neutrons, right? Then mass of the nucleons we have to calculate, and then also we have the measured mass of the nucleus, that is the rest mass of the helium nucleus also given here is 4.002604 am. So all the measured masses are given here in terms of am, atomic mass unit. Then mass defect delta m is equal to what? ZMB plus A minus ZMN minus the rest mass of the nucleus, that is the stable nucleus after forming the nucleus. That is major mass of the helium nucleus is given here in terms of. So what is the expected mass of the helium nucleus? That is the sum of mass of the nucleons. But here the major mass is this thing. Now let us calculate the difference. If the difference is 0, then there is no loss of mass. Then mass defect is 0. If we are getting some positive term between these two difference, then there is a mass defect. The mass is lost there, right? Therefore delta m is equal to 2 protons and 2 neutrons. 2 I will take common, then mass of protons plus mass of neutrons, right? So 2 times of mass of proton is 1.00726 plus 1.00865, right? So if you done the calculation of this, you will get the value is the 4.031812 am. This is equal to what? The this value. Now let us calculate the major mass of the nucleus. M is equal to what? 4.002604. The same we have to write here. 4.002604. So minus 4.002604. So the difference, so this term is bigger than this one, so we will get some positive term here, that in terms of AMU, that is equal to 0.0293 am. So this is what the mass defect during the formation of the helium nucleus from its constituent nucleus, that is 2 protons and 2 neutrons. So the mass is lost here, right? Some mass is lost here, right? Now you can convert this mass in terms of energy, that is in terms of what? The binding energy, right? So binding energy of the helium nucleus EB is equal to delta m into c square. We have to do here delta m into c square. Delta m here, it is this mass is in terms of what? AMU. You have to convert it in terms of kg. Then you have to convert. You have to multiply it for what? C. You have to multiply it what? C square. Right? Then you will get the energy in terms of joule. Right? Now one more point we have to study here before going to calculation of the binding energy by taking this example. What is electron volt? So you know that the energy, the SI unit of the energy is joule. SI unit of the energy is joule. But in atomic and nuclear physics, we are going to use here the one more unit of energy, that is electron volt. That is what? The electron volt. Right? Now let us see what is electron volt. That is the unit of energy. Then we will calculate the binding energy of the helium nucleus in terms of electron volt. So now let us see what is electron volt. So what is electron volt? Electron volt, it is the energy gained by the electron when it is accelerated through a potential difference of 1 volt. Right? The electron volt means what? It is the unit of energy used in the atomic physics and the nuclear physics. You all know that the joule is also the unit of energy which is used. Now mainly we are going to use the electron volt in atomic and nuclear physics. And what is the electron volt here? It is the energy gained by, it is the energy gained by, it is the energy gained by an electron when it is accelerated through a potential difference of 1 volt. Or it is the kinetic energy gain when it is accelerated through a potential difference of 1 volt. Right? So 1 electron volt, how we are going to define it? Right? 1 electron volt. So here is the E means what here? The charge of the electron, and V is what? The potential difference. Potential difference is 1 volt and E is the charge of the electron. So E is equal to charge of the electron is 1.6 into 10 to the power minus 19 and V is 1 volt. So 1 electron volt in terms of joule is given by 1.6 into 10 to the power minus 19 joule. So this is the relation between what? This is the relation between what? The energy relation. 1 electron volt, it is equal to energy in terms of joule. It is equal to 1.6 into 10 to the power minus 19 joule. So 1.6 into 10 to the power minus 19 joule, it is equal to 1 electron volt. Right? And 1 electron volt, it is the kinetic energy gained by an electron when it is accelerated through a potential difference of 1 volt. 1 volt potential difference ತಗೊಳ್ಳೋದಾಗ electron accelerate ಆಗ್ತಾ ಹೋದಾಗ ಅದು ಎಷ್ಟು ಎನರ್ಜಿ ತಗೊಳ್ತೈತಿ kinetic energy ಅದಕ್ಕೆ ಏನಂತ ಕರೀತೀವಿ ನಾವು ಅಂದ್ರೆ 1 electron volt ಅಂತ ಕರೀತೀವಿ. Right? Now how we are going to give the relation between this mass and energy? ಅಂದ್ರೆ 1 AMU ದಷ್ಟು ಮಾಸ್ ಲಾಸ್ ಆಯಿತು. 1 AMU ದಷ್ಟು ಅಮೌಂಟ್ ಆಫ್ ಮಾಸ್ ಲಾಸ್ ಆದಾಗ ನಮಗೆ ಎಷ್ಟು ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಎನರ್ಜಿ ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತೈತಿ ಅದನ್ನ ನೋಡ್ಕೋಬೇಕಾಗುತ್ತೆ. ಸಪೋಸ್ ಈಗ 1 ಮೆಗಾ ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಅಂತಂದ್ರೆ ಎಷ್ಟು ಆಗ್ತೈತಿ ಈಗ? ಸೊ 1 ಮೆಗಾ ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್, ಮೆಗಾ ಅಂದ್ರೆ ಎಷ್ಟು? ದಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು m is equal to 10 to the power 6, 10 to the power 6 ಇದಕ್ಕೆ ಮಲ್ಟಿಪ್ಲೈ ಮಾಡಿ 1.6 into 10 to the power 9 minus 19 into 6. So this is 1.6 into 10 to the power minus 13 joule. Now let us see here 1 AMU just amount of mass loss right under. Suppose 1 AMU amount of mass is lost or mass defect is observed. What is the amount of energy that is converted in terms of electron volt or mega electron volt? Let us calculate here first. Right? So now let us see the relation between, I think it is a simple point, it is understood what is an electron volt, which is the unit of energy used in atomic and nuclear physics. Now let us see the relation between AMU and electron volt. Right? Electron volt and AMU. 1 AMU is equal to how much electron volt or mega electron volt after. Let us see here. That is also an important derivation we have to discuss. Right? Now 1 AMU in terms of kg is equal to what? 1.66 into 10 to the power minus 27 kg. Right? Now let us calculate here. E is equal to mc square. ಈಗ 1 AMU amount just ಏನಾಗಿದ್ರಿ mass loss ಆಗೈತಿ, ಅದು ಎಷ್ಟು amount of energy ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತದೆ. So according to this relation, E is equal to mc square. So AMU we have written in terms of kg here, right? 1.66 into 10 to the power minus 27, and here C is the velocity of light, that is 3 into 10 to the power 8, 3 into 10 to the power 8 whole square, right? 3 c square, 3 into 10 to the power 8 whole square. Now multiply these two, you will get some answer that is equal to, so exactly the velocity of light we have given round up here by rounding up to 3, but its exact value is equal to 2.9979 2.9979 into 10 to the power 8 square. So this value we are getting in terms of joule. In terms of joule dolog bardite namgida. Afterwards we have to convert it in terms of electron. Now you multiply this. After multiplying these two, you will get the answer is. So you have to multiply these two. It is in terms of joule. We know that 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. That means this much joule. It is the amount plus joule later number. Now that will be converted in terms of electron volt. Electron volt we have to divide it by what? Joule to electron volt. We have this much amount of 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. But 1.66 into 10 to the power minus 27 this term, right? You do it as a homework. Multiply these two and solve it, and then divide it by 1.6 into 10 to the power minus 19. So after solving this, you will get E is equal to 931.5 into 10 to the power 6 electron volt. Right? So first thing E is equal to mc square. 1 AMU amount of mass loss aitandre adu ಎಷ್ಟು amount of energy ಆಗಿ ಕನ್ವರ್ಟ್ ಆಗ್ತದೆ ಅಂತ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡಬೇಕು. AMU ಅನ್ನ ಫಸ್ಟ್ ನಾವು kg ಒಳಗೆ ಕನ್ವರ್ಟ್ ಮಾಡ್ಕೊಳ್ತೀವಿ. Because of what? To write the energy in terms of joule. ಇಲ್ಲಿ kg ಮತ್ತೆ meter per second ಅದೇನಾಗ್ತಿದ್ರೆ joule ದೊಳಗೆ ಬರ್ತದೆ ನಮಗೆ ಎನರ್ಜಿ, ರೈಟ್? ಸೊ therefore ಈಗ joule ದೊಳಗೆ ಬಂದ್ರೆ ನಮಗೆ ಅದನ್ನ ನಾವು ಏನು ಮಾಡ್ಕೋತಿದ್ದೀವಿ, joule ಇದನ್ನ ಎಲೆಕ್ಟ್ರಾನ್ ವೋಲ್ಟ್ ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡ್ಕೋತಾ ಇದ್ದೀವಿ ಎನರ್ಜಿ. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So then this much amount of joule ಅಂದ್ರೆ ಎಷ್ಟು electron volt ಆಗ್ತದೆ, ಅದಕ್ಕೆ ನಾವು ಏನು ಮಾಡಬೇಕಾಗ್ತದೆ, divided by 1.6 into 10 to the power minus 19 ಮಾಡಿದ್ರೆ ಅದು electron volt ಒಳಗೆ ಕನ್ವರ್ಟ್ ಆಗುತ್ತೆ, ರೈಟ್? So then 1.6 into 10 to the power minus 19 roll ಮಾಡಿದ್ರೆ ಎಷ್ಟು ಬರ್ತದೆ? So that you will get it as what? 931.5 into 10 to the power 6 electron volt, or this is equal to 931.5 mega electron volt, right? However, in 1 AMU is equal to ಎಷ್ಟಾಯ್ತು? 931.5 mega electron volt. So this is the important relation between what? AMU and electron volt. 1 AMU is equal to 931.5 mega electron volt, right? So then ಈಗ ನೋಡಿ ನಾವಿಲ್ಲಿ ಹೀಲಿಯಂ ನ್ಯೂಕ್ಲಿಯಸ್ ಫಾರ್ಮ್ ಮಾಡಬೇಕಾದ್ರೆ ಅವಾಗ ಎಷ್ಟು ಮಾಸ್ ಡಿಫೆಕ್ಟ್ ಬಂದಿದೆ ನಮಗೆ? ಹಿಯರ್ ವಿ ಹ್ಯಾವ್ ಗಾಟ್ ದ ಮಾಸ್ ಡಿಫೆಕ್ಟ್ ಆಸ್ 0.0293 AMU just by multiplying 931.5, right? So mass defect or the binding energy of helium nucleus EB is equal to 0.0293 into 931.5. So this is you will get around 28 mega electron volt. 28 mega electron volt. So binding energy of the helium nucleus is the 28 mega electron volt. So with all these discussions about the Einstein mass energy relation, then mass defect, then what is the nuclear binding energy, and the calculation of mass defect taking an example of the helium nucleus, and the relation between 1 AMU in terms of the electron volt in terms of energy, that is the relation between the units of the mass, right, AMU in terms of the unit of energy, electron volt. So 1 AMU is equal to what? 931.5 mega electron volt energy. So 1 AMU mass is equal to energy, it is 931.5 mega electron volt, right? And then what is binding energy? That is the amount of energy required to bind the nucleons to bind the nucleons to form the stable nucleus, or it is the amount of energy required to break the nucleus into its constituent nucleons. With all these discussions, we will discuss the next points related to this concept, that is what is the nuclear specific binding energy and the nuclear forces. All those things we will discuss in the next class. So the one homework for you, that calculate the mass defect and the nuclear binding energy of the nuclear binding energy of the nitrogen nucleus, that is N740, right? So the mass of proton and the mass of neutron, it is given here. Then you note down the mass of the nitrogen nucleus. Mass of the nitrogen nucleus, that is equal to what? In terms of AMU. In terms of AMU, it is given by 14.00307. 14.00307 AMU, right? 14.00307 AMU. It is what? The rest mass of the nucleus, that is M is given here. By using this, and also you know that I already written in the board, it is the mass of the proton and the masses of the neutron. So by using the mass of the proton in terms of AMU, by knowing the mass of the neutron in terms of AMU, and here the rest mass of the stable nucleus is given in terms of AMU. By using all those values, you calculate the mass defect of the nitrogen nucleus, and also calculate the binding energy. Also calculate what? The binding energy, nuclear binding energy in terms of mega electron volt. So one important point what you have to understand here, the more is the binding energy, more stable is the nucleus. So that is the important point. That means what? The binding energy, what is the consequence or the important significance of this? The binding energy is which gives the stability of the nucleus. So one more question they may ask here. What is the important significance of the nuclear binding energy which gives the stability of the nucleus? More is the binding energy, more stable is the nucleus. So with all these points, we will continue in the next class and do it as a homework. For N740, calculate the mass defect and the nuclear binding energy in terms of mega electron volt. And this question was asked in March 2014. March 2014, they were asked to calculate the mass defect, nuclear binding energy of this nitrogen nucleus. So, okay, thank you so much.